the element constraint is this one. So you are given an array T of integer values, and then you have the domains X and Y. Okay, so this is like this. I will reduce slightly. So you are given an array T. You have the variable X, you have the variable Y, and you want to have the relation that is always satisfied T indexed by the variable X and Y equal to Z. And this is really what we needed for modeling the quadratic assignment problem. Okay, so this is my array T that is represented here. Here I have the variable X and I've got the variable Y. How to create an efficient propagator for this constraint? It's quite difficult to implement. So what we will do, we will use a small relaxation. We will decide not to create any holes in the domain of Z, but we are willing to possibly create holes in the domain of X and Y. And so this is not really domain consistent filtering. This is not really bound consistent. This is something in the middle of the two. Okay, but it's quite efficient in practice. So the way we will do that is that we will first use this small example, of course, to illustrate how the filtering algorithm is working. But we will also create a big table like this one, where we will create every possible combination for Z, X, and Y. Z, this is the target variable that you have here. Okay. X is equal to 2, Y is equal to 1, and Z is equal to 8 here. Okay? Sorry, so 2, 1, 8. Where is it? 2 for X, 2, 1, 8. Okay, so this is this row that you see in the table is this entry. Okay, so 2, 1, 8. You do that for all of them, and then we will sort according to the variable Z. We will sort them, okay, from the lowest value to the largest one, okay? So this is more or less a database representation. This is exactly a database representation of this two-dimensional array, right? Okay, and these are the domains. And what is important is that we will keep two pointers. We will keep the low and the up pointer, which means that every entries in between here are considered as support, as valid tuples by the constraint. Okay, sorry, I will do like this. So everything in between here is considered as a valid support. Okay, and now what happens is that the domain of Z has just changed. Okay, you see that it used to be 9 and now it's 7. So what we need to do is that we need to update this up pointer because 9 is no longer a support. And so we will go up until here, where we find again a support. Okay, because 9 is not a support, 8 is not a support neither. And so we will update like this. Sorry, I will come back here. Yes. Okay, this is what we do. What I also should mention is that here, we will have counters. So we have counters that count the number of column supports and the number of row supports, which means this is the number of entries in the table between the rows and the up, okay, in this line, in this line, in this line, and this is the number of entries in the column that are still in between. Originally, of course, we have 4 everywhere because it's everywhere because it's a 4x4 table here. T is 4x4, okay, right? So now it's 7. What we need to do is that we need to update the lowest pointer here up to here. And this is what we do now. Okay. So we update, but while we are updating, okay, this one is no longer a support. And so we will also update the counter here. Okay. You see that because this one is not a support anymore, 931, I put it in gray and I decrease here. This one by 3 is now 3 and this one becomes 3. And so on and so on. I update like this, okay, until I find a support again, okay. So here I need to increase because 9 is no longer there. I need to go at least up to here. This is what I do. And you see that I'm updating the counter. And now something interesting happens because the counter here has become 0. It means that this row no longer has a support, and it means that I can remove this value 2 from the domain of X. And this is what I do. Okay, I continue like that. Okay, no, it's fine. But again, you see that a 0 appears here in the counter of the column support. And so I remove the corresponding value 1, corresponding to this column in the domain of y. Okay, now the minimum has changed. It's no longer 0, it's 2. And so I will increase like this up to here. I will update the counters. Okay, and again, some 0 might appear, as it was the case here. And in that case, I remove this value 0, because if I have a 0 in one of the counters, I need to remove that. Okay. And so on, and so on. I think you've got the idea. And so you will really shrink the low and the up. And every time you increase low and up, you possibly update the counter. And when a 0 appears somewhere, you remove it from the domain of x or y. Okay. The question is, this is very nice. This works as long as you are decreasing in the search tree. What about the backtrack? If you want to backtrack, you need to restore the state of the constraint, because what I just explained is something that is very incremental. You can just update the low and the up, and they can only get closer to each other. But on backtrack, you need to restore all the values in this table. And so what you need to do that, you can already expect the answer will be, is that you need to have this as state integer values that is able to restore itself on backtrack. And it's the same for all the counters that you have here. Okay? And if you have that, the state will be restored by itself. So again, you've got two reversible integers for maintaining all the counters and the lower and the up pointers. I'll let you look in the source code. This is not too difficult once you understand what I just explained. Okay. If you look at the propagate, you see that you have this while loop that is really getting the two low and up pointers next to each other. And every time you do that, you update the support, and update the support just means that you will decrement the counter. And when a counter becomes 0, you just remove the corresponding value from the domain of x and the corresponding value from the domain of y. And so it's a very nice and elegant filtering, very efficient, because it's very incremental as well. In the next video, I will explain the one-dimensional element constraint.